Right, hello everyone. We're going to be looking at a problem on 2D rigid body equilibrium, and in this problem we're going to have a rigid body supported by a pin at one end and a roller at the other end. So here is the problem. So I have a rigid body. It's a straight beam whose width and thickness are of not much of a consequence to us. So here is a rigid body, and then I have a pin support at one end. So here is a pin support pinned here, and then I have a roller or a rocker support at the other end. So this is the entire rigid body. So the roller support at the other end is drawn as follows. It looks similar to a pin sometimes, but watch out, it's essentially like a pin on roller skates. So you see a set of small rollers that are given here, and this is on horizontal ground. So this is a pin support, and this is a roller support. Sometimes the roller will be drawn as a roller with a unilateral constraint, or we could have a rocker drawn there instead of a roller, but they all perform the same role. And now this rigid body is loaded as follows. So there are a set of forces and a couple moments which are acting on this rigid body. So first of all, I have a couple moment whose magnitude and sense are given to us. So this is clockwise with a magnitude of 250 Newton meters. Then I have a force of magnitude 200 newtons, which is acting at the end of the beam here. And then one more force which is acting right on 2 meters from the point A, and it has a magnitude of 300 newtons, and makes an angle of 30 degrees with the horizontal. Some distances are also given to us. Distance from let's call this end as end A, let's call this as point B where the force is acting, and let's call this as C. So from distance from A all the way to point B is given to us as 2 meters, and then to the end C from the point B is given to us as 1 meter. Alright, so we have a rigid body ABC. It is pin supported at one end, it has a roller support at the other end, and these are the loads which are acting on the rigid body. Couple moment of 250 Newton meters, a force of magnitude 300 newtons acting at an angle of 30 degrees with respect to the horizontal, and then a force of magnitude 200 newtons acting vertically downwards. And what do we need to find out in this problem? We need to find out all the support reactions. Okay. So first of all, draw a neat labeled free body diagram, and then find all support reactions at A and C. Alright, towards finding the support reactions, we first need to draw the free body diagram. And before we draw the free body diagram, let us very briefly review what a pin does, or how a pin constrains a rigid body, and then how a roller constrains a rigid body. And then based on that, we can draw the free body diagrams. Alright. So we'll look at a pin support first. I'm going to look at an isolated pin without worrying about the rest of the rigid body. So here is an example of that. Isolated rigid body. We don't care what's happening on that side. And then on this rigid body I have a pin which is drawn here supporting the rigid body. Now we want to see what are the ranges of motion that are possible on this rigid body. And you can obviously see that if I have a pin here, so this is a rigid body by itself. So if I have a pin here, then it is possible for me to rotate the rigid body in this particular sense. So I can rotate the rigid body. So if I set up an x and a y coordinate system here, let's say that this is x and y, this is x and this is y, and then I have a positive sense of rotation here. You see that I can perform the rotation of the rigid body about an axis coming out of the board or into the board, or out of the page or into the page, which means that motions of the following type are not constrained. So this is perfectly fine. But then what does a pin constrained? So if I look at the pin here, so this is the pin support. If I look at the pin support prevents me from moving up and down, which means that motion about the y-axis is not possible. Now the pin also does not allow me to move along the horizontal direction, which means that I cannot move in this direction either, which means that I have constraints along two directions. I'm allowed to rotate, which means that if I draw a free body diagram of the rigid body now and look at the effect of the pin is to produce a force of constraint in the x and the y directions. So if I draw the rigid body, I don't care about what's happening in the rest of the rigid body. So if I look at the point A, if I call this as the point A here, then I see that there are two forces of constraint, one of them in the y direction and one of them in the x direction. And the basic idea is that on the free body diagram we draw the effect of the pin by showing what are the constraints the pin produces on the rigid body, and the only constraint the pin produces here is that it does not allow me to translate along the x-axis, neither does it allow me to translate along the y-axis. And so I'm going to have these as the forces of constraint on the rigid body, and these will be the pin reactions. And pins need not be drawn this way, they could be drawn in the following manner as well. I could have the rigid body, we don't care about what's happening there. I could easily draw this pin in the following manner, and this is the same as that. So these are equivalent. And so the moral of the story is that in two dimensions, the effect of the pin on the free body diagram are two constraint forces, one of them in the x direction, one of them in the y direction. Now, is there any good reason for choosing them to be in the positive x and positive y? There is no good reason. You can easily draw them along the negative x and the negative y. We don't know. We will have to look at the total loading of the body in order to decide what the directions are. And thankfully, we don't need to spend our time thinking about what these directions are. Based on rigid body equilibrium, we might end up with a positive or a negative value, and that's perfectly fine. Let's look at a roller support, and then we will incorporate all of these aspects into our problem next. So roller support, rocker support, there are several ways in which these will be drawn. One of the common ways in which these are drawn is as follows. So we have roller support. Common ways of drawing roller supports. I'm going to draw two of the ways. The first one is what we have in our problem. I'm looking at an isolated roller support. The second one is typically what you will also see commonly done, and then perhaps the third way is by making use of a rocker element. So here we have a roller, first of all, the way drawn in your problem statement. We could also have a small marble of some kind which is placed on a horizontal ground. That's also an example of a roller support. Or I could have a rocker support in the following manner. It's like a point contact here. So this is an example of a roller. This is also a roller. This is an example of a rocker. And they basically perform the same functions, depending on, of course, how they are drawn. My aim is to look at the roller support in our particular problem. So if we look at that, I have the isolated roller support for our problem drawn as follows. So what are the ranges of motion possible for this rigid body? Once again, I set up a coordinate frame. I can have a positive x, positive y, and counterclockwise rotations are taken as positive. So what are the ranges of motion that are possible? You see that I can take this rigid body here. So in this picture, all of these are the rigid bodies. We have not shown the entire rigid body. We've just shown a small portion of the rigid body, which is perfectly fine. You see that here I can rotate it in the clockwise or the counterclockwise sense about the positive or the negative z direction which is coming out of the board. Also, it is possible for me to perform a translational motion. So these two are possible for me. You see that these are a set of wheels here, right? So which means that I can move them back and forth here, but I cannot move it up and down. So that kind of a motion is not possible, and that is a unilateral constraint, in a sense that in reality I can have this roller lifting off of the ground, but then I cannot sink into the ground further. And so that's a unilateral constraint. Sometimes you will also see rollers with a bilateral constraint. Example of that being you could have a rigid body here, and then you could have a huge roller element, and then it will be affixed with walls on both sides. So this will be a bilateral constraint, and this will be a unilateral. But either ways, for us, what is the moral of the story is that if I have a roller support, then I can perform rotational motions perpendicular to the plane of motion. I can perform translations along one particular direction, but I cannot translate along another direction. And so if I draw the free body diagram of the rigid body, and if I want to show the effect of the roller, or if I want to show the effect of the rocker, then I have to show a constrained force in the direction that motion is not allowed, or motion is constrained. And if I look at the rocker is also pretty much the same. It allows me to move in this particular direction. It allows me to rotate, but I cannot move up and down. That is not possible. Look at this roller element here. I can slide horizontally, I can rotate here, but I cannot sink into the ground. So this is an example of a unilateral constraint as well. We don't need to worry about the nature of these constraints. For us, most of the times, whenever you see a roller element in 2D, you have to keep in mind that there is one constraint force only, and this is in a direction that motion is not allowed. Okay, so if I have to draw the free body diagram of the rigid body and show the effect of the roller on it, then essentially this is what it's going to be. So here is the rigid body, and then all I have to show is a force in this particular direction. So this is going to be, if I call this as the point C, right? So this is going to be a force Cy. There is no sacred reason for choosing this to be in the upward direction. You can quite easily choose this to be in a downward direction as well, except that you see, if you have a unilateral constraint, then the force of reaction is always going to be in the upward direction. Bilateral constraints, it is quite possible that the force is going to switch directions, which means that we don't necessarily need to choose a Cy to be pointing up or down for a bilateral constraint. The way I typically think about it is, if I have a unilateral constraint, I know that contact out of this plane here is not possible, so my force of reaction is always going to be pointing in the direction of the normal to the surface the rollers are contacting, and that's going to be in the upward direction here. Alright, so we're going to take all of these, put this into action on our problem. So let's look at our problem. We need to draw the free body diagram. We had the rigid body, which was drawn as follows here. So here is a rigid body. Now on this rigid body, we know that there was a pin and a roller. The roller was at the end C. So just to take a look at the figure that was given to us. So here was the actual figure from the beginning of the problem. You see that there is a pin at the point A. So my first aim is to mark the support reactions at A. I'm going to choose them in the positive X and positive Y direction. So here is X and Y positive for me. So this is going to be positive Y, positive X, and I'm going to choose all rotations that are counterclockwise as positive. So I'm going to have an AY pointed this way, then I'm going to have an AX which is pointed this way, and then you see I have a roller here, unilateral constraint of course, so I'm going to choose a force roller reaction pointing in the upward direction, and I'm going to call that as CY. There is no CX for the roller because the roller allows me to translate along the x-axis here, and no reaction moments because we saw that by themselves rollers and rockers do not constrain any rotational motion, and so they allow you to rotate, which means that on the free body diagram you do not show a constraint reaction moment due to the roller or the pins. And then we will also draw the remaining ones, which are the forces and the applied loadings. So I have 250 Newton meter couple moment. Then I have this 300 Newton force. I'm going to break it into two components, 300 sine 30 and 300 cosine 30. So there's one here. This is going to be 300 sine 30, and then I'm going to have a component this way, which is 300 cosine 30. And then finally I'm going to have a force which is acting at the end of the beam, and this was 200 newtons. And then we had the dimensions which were given to us, all the way from here onto here was 3 meters, and then 2 meters, I'm sorry, and then this was going to be 1 meter. Alright, so this is the free body diagram. What are the ingredients of the free body diagram? I have the reaction forces, all the reactions that are shown, then I have the applied loadings as you can see, and then I have the dimensions, and then I have a coordinate system where I choose things to be positive pointing to the right, things are positive pointing up, and then counterclockwise rotations are positive. And that's about it, and we start summing forces in the x, y, and we sum moments about a convenient point. So summing forces in the x direction, so we are going to say sum of all the forces in the x direction is equal to 0. All the forces pointing to the right are taken as positive. What are the forces? I have AX pointing to the right, then I see that 300 cosine 30 is pointing to the left, and that's about it, which means that all of these have to be equal to 0, which means that AX is going to be 300 cosine 30, or approximately 260 newtons. And then we come back and we sum forces in the y direction. So sum of forces in the y direction is equal to 0. Forces pointing upwards taken as positive. What are the forces in the y direction? I have forces AY and CY pointing up. So I have AY plus CY, then I have 300 sine 30 pointing down, and then 200 newtons pointing down, and all of these are equal to 0. Now be careful, when you do the summation of the forces, the couple moment will not play a role. The couple moment will play a role only when you do summation of the moments. And now you see that this equation here is not very useful because I do not know AY, neither do I know CY, which means I need to perform the summation of the moments about a convenient point. And here I can choose pretty much any point in the rigid body. Excuse me. But I'm going to choose the point A. You could very well choose the point C as well. Okay, so I'm going to choose the point A. I'm going to sum moments about the point A, set that equal to 0. I'm going to assume all counterclockwise rotations to be positive. So what are the moments about the point A? I start with the forces at the point A. They do not cause a moment because they're sitting at the point A. Then I see 250 Newton meters clockwise, which means that's going to be a minus 250. Then I see that the 300 cosine 30 has a line of action passing through the point A, so it does not cause a rotation. 300 sine 30, perpendicular distance of 2 meters, look at the right hand rule applied, produces a moment in the clockwise direction, so 300 sine 30 times 2 meters in the clockwise direction, so that's minus 300 sine 30 times 2, Then I have the 200 Newton force. Look at the 200 Newton force. Perpendicular distance all the way from the point of interest to the line of action is 2 plus 1, 3 meters here. Right hand rule produces a moment that is also clockwise. So this is 200 times 2 plus 1, 3 meters. So that's going to be minus 200 times 3. And then the last one is Cy. Look at Cy. Cy has the same perpendicular distance as the 200 Newton force, but then it is pointing in the upward direction. So if I use the right hand rule, my palm faces the point of interest, which is A. I curl my fingers, comes out of the board, so Cy times 3. So plus Cy times 3. All of these put together is equal to 0. And you see that the only unknown here is Cy. I can solve for Cy. Is going to give me 383 newtons, approximately 383.33 newtons. And so once I find Cy, I can go back, use the summation of forces in the y direction, and I can find Ay. And Ay will end up being minus 33.3 newtons. And in these problems, it is quite a plausible step in order to do the summation of the moments first before you do the summation of the forces, because you obviously see that, okay, this is not a very useful equation, so I don't want to spend time writing this out first and then thinking, okay, this is not a good procedure. So I typically do the summation of the moments first. I find out one of the unknowns directly, and then once I know one of the unknowns, I can then plug it back into this equation here, and I can find Ay from there. Okay, thank you.